Last two questions on the 3.2 worksheet. Solutions here. Number 16 is liquid oxygen at its boiling point is stored in an insulated tank. Gaseous oxygen is produced from the tank, blah, blah, blah. Now, you may not already know this, but gaseous oxygen is actually the O2 molecule. If you're doing chemistry, you might be familiar, but if you're not learning chemistry, then you may not know this. That is why mass of 1 mole of oxygen is given as 32. Do you have to know that that means O2? No, not really, because we're already given that 1 mole is 32. But if you do know oxygen as an atom, it has a mass per mole of 16 grams, but we're giving 32. So you might get confused if you know oxygen has a molar mass of 16, but it is given as 32 because of this detail. Again, do you have to know that oxygen gas is O2 molecule? No, not really, as long as you use this information correctly. We are given 1 mole of oxygen is 32, and we're given the specific latent heat of vaporization. So this is LV. Okay, the first part is asking us to explain a case, distinguish between internal energy of the oxygen at boiling point when it is in liquid phase and in gas phase. I highlighted these terms because you know how we answer these explain worthy questions. It's 2 marks. You are meant to say two things, which means you have to find what keywords the question is giving you. So between the internal energy of the oxygen at the boiling point. So we need to first explain what is internal energy. You can simply define it by potential energy plus kinetic energy of the particles. Please write this as a sentence. I wanted to explain this quickly, so I didn't write it out, but when you write it in an exam, please write it as a whole sentence. And the second thing you can say is the difference between liquid and gas. That's what the question wants specifically. And that's why it says distinguish between. So you need to say a difference between the liquid and the gas phase in this given context. So what you can say is, if it's a real gas, it has no potential energy. You could if it's an ideal gas, let's correct that. I'm not going to record this again. I'll just fix it. If it's an ideal gas, assumed to be an ideal gas, it has no potential energy. If it's a real gas, which they always are, it has potential energy stored, but it has more internal energy, definitely, than the liquid because it had to gain energy to become gas. So its internal energy has to be more, which means it would have more potential energy. But if it is ideal gas, then all of that internal energy is liquid. Well, I'm sorry, all of that internal energy is kinetic. Now, you could also say liquid and gas have the same kinetic energy at boiling point. Obviously, they're at the same temperature. This calculation bit, now we're given flow rate. This isn't any of the terms that we use in our formulas, but looking at the unit, moles per second. So this is, use your common sense, 0.5 moles in 1 second. So you're going to need mole versus time ratio for this number. We are asking for power. What is power? Work divided by time. What kind of work is being done? Heat energy is being provided, and it's boiling. So we use ml. There is no delta T. We use the energy for without delta T. So mass times the latent heat divided by time. Then we ask which one of these do we know? We know the latent heat, which is this which is this number. The 0.25 times 32 is the mass. Why? Because 0.25 moles times 32 grams per mole. So If 1 mole is 32 grams, 0.25 would be 0.25 times 32 mass in grams. So we have the mass in grams here in 1 second. So for time, if I put 1 second, this is where the unit comes in handy. But you also have to write the 10 to the minus 3 here, because this is given per kilogram. So this is joule per kilogram, which means the mass you used must be in kilograms. So this is the conversion factor, and that's why you get this number. You always have to use SI units with SI units. If mass is given in grams, you have to convert that to kilogram to get an answer in joules. So just to explain again how I use this rate idea, I know that is given me number of moles per second. I just work out my calculation. I know I'm looking for power, that is work divided by time. Time I just keep as time, and work is energy added, so M times L, because it's at a change of state. So LV I already know, joule per kilogram, so I need the mass in unit time. But I know 0.25 moles flow in 1 second. So if I put 1 second for time, I know how many moles I can put here, but I actually need the mass, so I multiply that by mass per mole, and I convert it to kilogram. Calculation gives me answer. Then this part says in 1 second, calculate the volume of oxygen produced, and when it is allowed to expand to a pressure of 0.11 megapascals. So the mega is the 10 to the power 6. So 0.11 times 10 to the power of 6 is the pressure. I'm just following from the formula. So this is P. V, I don't know, so I write just V. N, number of moles. The question does say in 1 second, so I use 0.25 because that's the number of moles in 1 second. R is given in the data booklet, 8.31. This is an SI unit, so you don't need any conversion. And then 260 is again given in SI unit, Kelvin. And then the rest is calculation. And since we put everything in SI units, we will get the volume in its SI unit, which is meter cube. Part C asks one assumption of the kinetic model that doesn't apply to oxygen. Well, it's indirectly asking you to say one of the assumptions of the ideal gas kinetic model. So you can say one of the things of, like, they obey Newton's laws, they obey PV and RT, collisions are elastic, and there are no intermolecular forces, all energy is kinetic. Any one of these things will work because it's only one mark. Looking at number 17, we see a graph. First thing I'd like you to notice is what I highlighted on the labels on the axis. These are the numbers on the axis, but when you have a multiplier in the label here, you have to be alert to this. Physics questions do this a lot, and possibly chemistry as well. On graphs, make sure you look for any multipliers, because this isn't 2 pascals, this is 2 times 10 to the power of 5 pascals. Any number will have that multiplier with it, which means it has this for the volume as well. So those are the values given, and the point A, state A, a certain volume and pressure. Deduce the temperature of the gas in state A is approximately 300 Kelvin. So we know the number of moles. We have everything to put into the PV and RT. This is our P, this is our V, equals, this is our N, R is the constant. From the data booklet, T, and solve for T, you get about 332, which does approximate to 300 Kelvin. And then we move on to part B, where it's asking us to calculate a new volume once the temperature has changed. Now, there are 2 ways to do this. Since we know it is at constant pressure, and we know the value of that pressure, you might as well use that value and the number of moles, those are not changing, and simply substitute into PV and RT just like we did above. So this is the pressure, that is this number. We're solving for V, N is the same, and R is obviously the same. And T would be 900 in this case. You would solve for V. Or alternatively, in a question like this, say you don't know the pressure, you don't have a graph to read, or you're just not given that value, but you know it's constant. When pressure is constant, we know volume is directly proportional to the temperature. So you can simply use a ratio. Volume, initial volume, 8 times 10 to the minus 3. We know this from the previous part, where temperature is 300. We know that from this question. New volume will be proportional to 900. Well, temperature is becoming 3 times bigger, so volume will also become 3 times bigger. Simply you can get 24 times 10 to the minus 3 meter cube. Part C is asking for the work done. Now, we learned work to be area under a PV graph, which would be the change in the PV product, whichever one is changing. In our situation, P is constant, so I put that number here, and V is changing, and initially it's 8 times 10 to the minus 3, and final volume is 24 times 10 to the minus 3. So 24 minus 8, 16 times 10 to the minus 3 would be the volume change. Multiply that by P, and you get the work done in Joule. Now, this question is one from a previous syllabus. It's there because this question is from November 2008 session. You guys were pretty young back then, but the students who wrote that IB exams back then had to learn the laws of thermodynamics and much more. So I kept this question here just so you're aware. When you see questions like this, don't do it. I did say this in class, I'm reminding you. When you see a question in past papers older than 2015, which was the last session of the previous syllabus, if you see any questions asking for laws of thermodynamics, process types like adiabatic, isobaric, etc., a Carnot cycle, those are terms, concepts that have been removed. So in your syllabus, this question will not exist. I kept it here for the sake of reminding you that you don't do that question. Obviously, it won't be on any of your tests, but I kept it in your worksheet so I could remind you of this. Thank you.